This next bit also extends on our extension. So extension 2. Roots and coefficients, which of course we first saw in tune with quadratics. Extend it with polynomials. I mean, there's no new theory here. It's pretty much the same thing. You've got a polynomial, but now I'm saying of any degree. We know some of the roots 1 at a time will always be minus b on a. 2 at a time, c on a. 3 at a time, minus d on a. 4 at a time, e on a. And you can keep going and you keep going. And it's very rare they will give us a polynomial bigger than degree 4 for these questions. But the idea does flow through to other polynomials as well. A reminder, the alpha squared plus beta squared formula and the 1 on alpha plus 1 on beta, that's what we saw with the quadratic, but that does generalise. Some of the roots squared, so sigma alpha square means alpha squared plus beta squared plus gamma squared. Okay, so some of the roots squared will always be the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. Doesn't matter the degree of the polynomial. And when it comes to our standard algebraic fraction one, very hard to generalise a formula here because it changes. 1 on alpha, well, if there's only 2 roots, then it would be sum of the roots 1 at a time on alpha beta. If there was a cubic, it would be sum of the roots 2 at a time on alpha beta gamma. If it was a quartic, it would be sum of the roots 3 at a time on alpha beta gamma delta. But you'd always get that pattern. Just treat it like algebraic fractions, I guess, is the easiest way. Let's have a look at this cubic. X cubed minus 2x squared plus 3x minus 4. They want us to find, first of all, the standard ones, which even if they didn't ask, you're probably going to find anyway. You might not end up using all of them, but certainly some of them will come in handy for the types of questions they're going to ask us. Turns out to be, oh, look at that, isn't that nice? 2, 3, 4. Very nice. Alpha squared, so there's the standard alpha squared plus beta squared plus gamma squared. So sum of the roots 1 at a time squared minus 2 times sum of the roots 2 at a time. Sub in what we've just worked out, and we come up with minus 2 for this question. What about if it's the sum of the roots cubed? Now we got the sum of the roots squared formula from when we expanded out alpha plus beta all squared. We could do a similar thing. We could do alpha plus beta, but remember it's a cubic, so we've got 3 roots. Alpha plus beta plus gamma all cubed, expand the whole thing out, come up with a formula. But there actually is a smarter way. I know alpha is a solution to this cubic. So therefore alpha cubed minus 2 alpha squared plus 3 alpha minus 4 does equal 0. Well, the same is true for beta and the same is true for gamma. So if I think of them as 3 simultaneous equations, I can add them up and I'll get the sum of the roots cubed minus 2 times the sum of the roots squared plus 3 times the sum of the roots 1 at a time. And then with the constant, we just have to multiply it by 3, of course, because we've got the constant in each of the equations. So I end up with minus 12. And there's a little formula that will work it out for this particular question. Rearrange that, make sigma alpha cubed, that's what we want to find. Substitute in all the others we have found already. Substitute in and we get our answer of 2. Okay? And that's probably easier than trying to come up with some general formula for the sum of the roots cubed. Well, what about power of 4 then? Still use the same idea. Remember the equation was x cubed minus 2x squared plus 3x minus 4 is equal to 0. So in the last question I said alpha cubed minus 2 alpha squared plus 3 alpha minus 4 was equal to 0. All I'm doing is multiplying both sides of the equation by alpha. And so it now is alpha to the power of 4 minus 2 alpha cubed plus 3 alpha squared. And I'm going to do exactly like I did in the last question and say, oh, well, that was alpha. The same would be true for beta. Same would be true for gamma. And I'll add them up again. But now I've got sum of the roots to the power of 4 minus 2 times the sum of the roots cubed, and so on. So really, I don't have to go through all that. All I have to do is substitute into the actual equation. The only thing to remember is, if I'm left with a constant, I need to multiply by the constants by the number of roots. So in the last question, the minus 4 I multiplied by 3. In this one, I'm not left with a constant. And so it stays as minus 4 times the sum of the roots one at a time. So rearranging that one, subbing in. I guess this method has the disadvantage that in order to work out to the power of 4, I need to work out to the power of 3 and squared. Well, fortunately, we've already done that. Where I can sub in and we get 18 for our answer there. Alpha plus beta times alpha plus gamma times beta plus gamma. I guess the first reaction would be to expand the whole thing out. It's probably a sensible thought, but there is a quicker way. Alpha plus beta is the same as saying the sum of the roots one at a time minus gamma. And alpha plus gamma is the sum of the roots one at a time minus beta, and so on. Now, you've still got the same number of terms to expand out, but I can replace one of them with an actual number. So rather than having all, because when you think about it, when I expand that top one out, if I was to leave it like that, I'm going to have alpha, beta, gamma, alpha squared, beta, gamma, all sorts of mixtures. This one's going to be a lot nicer to substitute into. So I'm still going to have to expand the whole thing out, but the grouping is much nicer and easier to see. I get 4 times the sum of the roots one at a time, 2 times the sum of the roots 2 at a time, and just one lot of the alpha, beta, gamma. Don't know why I bothered putting the sigma on that one when you think about it, because there is only one term, which is alpha, beta, gamma, but anyway. Subbing in what we've found, 2 again. Gee, that answer's coming up a lot. The answer is not always 2, okay? So if you don't know how to do it, don't just write 2. 1996. Consider the polynomial. This time we've got a quartic. A, B, C, and D are all integers, so whole numbers, okay? Suppose the equation has a root of the form ki, and k is a real number, but it's not equal to 0. State, so here we are again, typical sort of extension 2 question. Let's see if you really understand what we're doing here. State why the conjugate minus ki is also a root. So they're looking for here that you understand that if all the coefficients are real, which they are in this case, solutions or imaginary solutions will appear in conjugate pairs. So if ki is a solution, minus ki must also be a solution, because we know they're going to appear in conjugate pairs. Show that C is equal to k squared RE. Well, in part A, they asked me to state why minus ki is a root. So maybe that's giving me a hint on how to do part B. So I factorised it. I know ki is a root, but I also know minus ki is a root. So there we are, factorised, k plus ki, k minus ki. And it must be times some other quadratic. And I know that other quadratic is monic, because we were told all these coefficients are integers. So I know it's going to be something like x squared plus px plus q. Span the whole thing out, and now that I'm looking at all this working out I've done, I'm wondering whether I could have just done some of the roots one at a time and things like that, because I think effectively that's what I'm going to end up with. So possibly that was a better way of approaching this question, but anyway. And then I've grouped the x cubes together, the x squareds together, and so on, and I'm going to equate the coefficients from the left-hand side with the right-hand side. So from this, the first thing I now know is, well, p is the same as a. I know q plus k squared is the same as b. I know k squared p is the same as c, and I know k squared q is equal to d. Now, what are we trying to get? C is k squared a, if we got it there. Yeah. Have a look at number 3. I've got c is equal to k squared p, and number 1, I've got p is equal to a. Combine those two together. So substitute 1 into 3, and we've got k squared a is equal to c. So there's that one. Show that c squared plus a squared d is equal to abc. So what did I do this time? The second one we came up with was q is equal to b minus k squared. Well, that's it rearranged anyway. The fourth one then, if I sub that in, I'll get k squared b minus k squared is d. bk squared minus k to the power of 4 is equal to d. What have I done? Oh, of course, because we said k squared is c on a. Or well, we didn't say it that way. We said c was equal to k squared a. But if I substitute in for k squared, I now have bc on a minus c squared on a squared is d. Multiply everything by a squared. I've got abc minus c squared is a squared d. That looks like the same thing, isn't it? Just got to rearrange some terms. And there we go. C plus a squared d is ABC. Gotta love algebra manipulation, don't you? So much fun. If 2 is also a root of the equation, and in addition b is equal to 0, show that c is an even number. So that means we know that ki is a root, minus ki is a root, 2 is now also a root. So there's one more root. Let's call that fourth root alpha. So alpha is the fourth root. Now we know ki minus ki and 2 are all integers or integer multiples. We also know that the sum of the roots is an integer. So therefore alpha, our fourth root, must be an integer. Because if the answer is an integer, and the other three roots are integers, the only way we could add a fourth root and get an answer of an integer is if it is also an integer. There we are. I've done sum of the roots 2 at a time. That's going to equal b. Why did I pick b? Because they told me b was equal to 0. So that's why I've done 2 at a time. I end up with k squared is minus 2 alpha. But remember, alpha is an integer. All right, so that came from my c is k squared a. C is equal to 2 times m. Alpha is an integer. A is an integer. Therefore, m must be an integer. 2 times an integer is an even number. Okay? So I went and showed k squared was equal to minus 2 alpha. But also back in C, we said C was equal to k squared times A. So C became minus 2 alpha A. So minus 2 times something, this thing m. But alpha and A are both integers, so I know m is an integer. 2 times an integer is an even number. Ta-da! Thus C is an even number. As we now know, it's divisible by 2. Yeah, that's just one approach. I'm sure there are other ways of handling that particular question. Okay. You'll never guess which questions we're going to do.